Right, good morning. So, after some gap, I'm back. So, I was away yesterday and on Saturday. So, today and tomorrow, uh, how's your project coming along? You are probably doing some sort of project, right? Did you finish yet, or there are awards, right? Okay, so we looked at a lot of materials, right? Especially functional materials, and we looked at how these functional materials or their functions that we desire change based on the crystal structure, based on the atomic arrangement, based on how we process them, right? So of course, when you process them, you change you change parameters within the crystal structure, within the morphology, within the microstructure. That's why you get different properties. And when you can change in a specific model or in a specific way, now you know how to control or how to get the properties you want by changing the parameters. And now we have new techniques to make materials in different shapes, and without having to involve human intervention, or without manually doing it. It's all automated. You can print any structure. That is the beauty of additive manufacturing. So you can put it for printing and go and come back, and you have a specific geometry and structure. So, but then when you print them, can you retain those properties? Now you have to optimize the parameters within the additive manufacturing process, right? So, but for functional materials, it's slightly, you have additional ways you can control the properties of the functional materials, right? And I specifically talked about this magnetocaloric material that heats up when you apply magnetic field. So if it heats up when you apply magnetic field, then you can use it. It's a reversible process. So if you take down the magnetic field, it cools down, right? So if that is the case, we can use it for refrigeration or air conditioning and so on and so forth. Because it's more efficient, and instead of compressor, you use magnetic field, which is turn on and turn off magnetic fields. So you can get heating effect more efficiently. But now the problem is, if you take a bulk material, apply magnetic field, it heats up everywhere, right? Inside as well. But if it heats up, you have to cool it down to room temperature to remove the magnetic field. If you want to remove the magnetic field and cool it below the room temperature, you have to first take it to room temperature, right? That means you have to cool down this hot material to room temperature. But if it's a thick solid, you can't cool it down, right? You have to make channels through it, small holes through it, so that you can pump in water or fluid so that it cools down. Otherwise, it will stay hot like that for a long time. And by the time you bring it to room temperature, it's like a couple of hours have passed, and then you can further cool it down below room temperature. But to speed this process, you need to create what are called as microchannels, right? Otherwise, it won't cool down to room temperature. It will take forever. So we need to do this several times per minute so that we can have higher cooling effect. So for that, we need to use additive manufacturing to make these channels, microchannels or pores, so that we can cool it down. So in order to do that, If you want to do microchannels, then you have to either make it as a wire or make it a powder to use additive manufacturing, right? So that means first you have to make powders of these functional materials or wires of these functional materials. So we have studied the bulk materials quite well of this one such functional material, which is magnetocaloric material. We have also deposited thin films. Thin films is kind of additive manufacturing, but at a nano level, right? So we have done that. And now we have also done nanoparticles of it. So that means we have powder now. We have used ball milling to make this powder. That means we have high yield of these powder. We can make lots of these powder so that we can use it in additive manufacturing. So now let's see how we can do this. But when we started this work, we did not have a lot of additive manufacturing facilities. So we had to first do inkjet printing. Then we had to do direct ink writing, polymer assisted material, 3D printing. And then now recently we are doing what is called as lens. This is using laser and then the powder. Okay. So, but for that, just a quick reminder how this material looks like, right? If you want to use any material or process any material, first you need to understand what phase it exists in. If you change the temperature, what happens to the material, right? So first you have to understand the phase diagram of a material in order to know how to process that material. So here is a phase diagram. Normally, the phase diagram that we see is here. If it's a binary, you have 2. If it's a ternary material, you have 3, right? So this is a binary phase diagram. And you have the composition here at the bottom. And in normal phase diagrams, you usually find, what do you find here in phase diagrams on y-axis? In materials, in a phase diagram, what do you find on y-axis in normal phase diagrams? Temperature of, so what does it represent? Here it is, this is also temperature, right? So in normal, this is for magnetic materials. This temperature is magnetic phase transition temperature. That means at these temperatures here, the material becomes paramagnet if you heat it up. Otherwise, at low temperature, it is ferromagnetic. So this is magnetic phase diagram. But in normal phase diagram, what do you have? What will this line represent? Still transition temperature, but what transition? Phase, right? Liquid to solid or one solid to another solid. So this is still phase transition temperature. Here it is magnetic phase. In normal materials, it will be structural or liquid to solid phase, right? So here is a magnetic phase transition phase diagram of this material, gadolinium gadolinium silicon germanium, okay, or gadolinium germanide and gadolinium silicide. So if you start to add silicon here, and then if you completely replace germanium with silicon, you get higher transition temperature, which is about close to 350 degrees, 350 Kelvin, which is about 60 to 80 degrees centigrade, right? So as we replace germanium with silicon, we are increasing the magnetic transition temperature. So, but we want to use this for room temperature purposes. So that means we want to be somewhere here, right? This is the magnetic phase diagram. Now, We wanted to be on safer side, because when you are at 260, 70, you may, if you want to characterize these materials, you may not be able to cool it down to lower temperatures. You might have to operate at room temperature. A lot of the characterization equipment will have the facility to cool down the material to do all sort of measurements, but not all of them will have. So we wanted to be on safer side. So we thought we'll do gadolinium completely silicide, which has a transition temperature of about 340. So we'll only do gadolinium silicide so that it's completely magnetic at room temperature. Okay, so and it's also completely binary phase, so which means it's easy to work with. We don't have to worry about germanium, and germanium is also expensive. So if we work on this material and figure out everything for additive manufacturing, we can always go back to other compositions, right? So that was our aim. So we did most of the work on this composition. So now, what do we want to do? So we want to first make powder of it, right? So powder, so that means to make powder, first you have to make the material, gadolinium silicide ingot. Basically put gadolinium, silicon, heat it up, 2500 or 600 degrees, that is the melting point of gadolinium, and silicon has slightly lower. So when you heat it up, both become liquid. It's called arc melting, right? You use an electric arc to melt. It's a common technique in laboratories. And you can also make smaller quantities. You melt both the materials and mix it with the arc or a stirrer, and it becomes a stoichiometric compound of 5,4, gadolinium 5, silicon 4. Sometimes what happens is, if the melting points are too different, if silicon had very low melting point, then it may reach its boiling point by the time you melt gadolinium, right? This is not the case here, but if you used germanium or indium, so you may reach boiling point. If you reach boiling point, some of the vapors go away, right? Then you won't have the same amount of silicon left to make a 5,4 compound, right? Then you get off stoichiometric compound, right? You won't get the same compound, 5,4. So that's one of the issue. When the melting temperatures of the two materials are not close to each other, then you may have to add a little extra so that you can account for whatever gases out. Okay, so that's again, it comes by experience. How much? It depends on the vapor pressure. There is a science to it, and you add, based on the vapor pressure, you add some additional material so that you get exactly 5,4. Okay, otherwise you may get 5,4 and a secondary phases of 5,3. If you look in the scanning electron microscope, you'll be seeing some small residual phases of 5,3 or 1,1, gadolinium 1, silicon 1, or gadolinium 5, silicon 3, residual phases in the material, right? So you have to maintain the right stoichiometry. Once you have this ingot, and you do thermal treatment to get the monoclinic phase. Okay, so once you get that, once you do the annealing, you do the ball milling. So you have ball milling here. So this is the material, the powder that you get. And you can use this powder for additive manufacturing. In here, we further size selected it. Actually, if you have this wide distribution of particles, sometimes it's helpful in some additive manufacturing techniques, sometimes it's not. So for biomedical applications, you need to have narrow size distribution, meaning the particles should be of 50 to at most 60 or 50 to 70 nanometers. But if you have 10 nanometers all the way to 1 micron, then you have wide size distribution. If there is wide size distribution, then the properties also will vary. So you don't want that. So you do size separation. Once you do size separation, this is again for biomedical applications. I'm not going to talk about this. We do other things like take a nanoparticle and coat a shell on the nanoparticle. And once you have a shell, you get more exotic properties, interesting properties, which are used in biomedical applications. Okay, I'm not going to talk about this. This is another part of our study. But the point I want to highlight is you use arc melting, make a big ingot, make sure it's chemically pure, like it has 5-4 phase, and then anneal it, and then make powder out of it. Once you have the powder, then you can do the powder bed fusion, or you can use lens. You have looked at that, right? Lens is laser energy net shaping, right? Lens, yeah. Powder bed fusion, you need lots of powder to make a shape, so you use it in these techniques, right? So here in this graph, you see that if we take the ingot, this ingot, and mill it, keep milling it for long duration, it completely loses its magnetization. That means it's becoming amorphous. There is no crystallinity. If there is no crystallinity, then some materials lose magnetization, because remember, the magnetization comes from unpaired spins, right? So that spin might not, if you don't have the crystal structure, it may not be able to retain that unpaired spin. It may all, again, recombine. The spins might pair with the other unpaired spin and lose magnetism completely. Okay, so here are the particles in an SEM, scanning electron microscope. How many did you see scanning electron microscope here? Yeah, you saw here, right? Was it shown to everyone? Oh, 3D scanner, not. So SEM stands for scanning electron microscope. So what happens in scanning electron microscope is you take a filament, apply really large voltage to it. We're talking in terms of 200 kilovolts, and again, very small current, but the voltage is very high. At that high voltage, the electrons will start to come out of that material, so you get a beam of electrons. Again, you use some electromagnetic coils to focus it and accelerate those electrons, and when these accelerated electrons come, they hit the sample. When they hit the sample, a lot of them are reflected back from the nucleus of the material, and some of them are reflected from the surface. Some go to 2 nanometers depth, some go to 15 nanometers depth. Depending on how deep they go, you get different type of scattered electrons. And some electrons, they go strike the electron of the sample, and the electrons observe that it's complete elastic scattering. So that means the electron comes and hits this electron, transfers all the energy of the outer electron, and that electron goes to the next orbit. But that's not its stable state. It immediately comes back to its ground state. What happens when the electron falls back to its stable orbit, ground orbit? What happens? It emits something, energy, right, in the form of a phonon, a photon, or an X-ray. X-ray is again photon, but photon could be within the visible white light or in X-ray spectrum. So in this case, it emits an X-ray, and that X-ray, the energy of that X-ray depends on what orbit it is. So that Means if you know how much energy X-ray it is emitting, you can know what material is in that sample. Okay, so that's how you can identify all the elements that the sample has. That is called EDS or EDX, both are EDS or EDX, energy X-ray diffraction spectrometer. Okay, so you can, by SCM, using SCM, you can know exactly what element is there in your material. So we do this to make sure that whatever material we have is the same. And also, for example, if you do it here, you can make a mark here, and the electron strikes only in this particle, and it will give you the elements in this particle. It will say it has 5 atoms of, I'm just making it up, it doesn't say 5 atoms, it gives in terms of percentage. Okay, it will say so this is 60% gadolinium and 40% silicon. That means are 55 and 45%, 55% gadolinium and 45% silicon. That means I know it's gadolinium silicide. But if it said it has 50% of gadolinium and 50% of silicon, that means I know that it's a different phase. It's off stoichiometry, or it's not gadolinium 5 silicon 4, it's gadolinium silicon. Okay, so that's how I can know what phase it has formed. Okay, and also the contrast of this will be different from the contrast of the other. In this case, it looks like they're similar contrast, and we have also done the EBSD, so it gives you a table of atomic percent. So we know that these are all gadolinium 5 silicon 4 particles. Okay, so you can do elemental analysis, and you can do morphology. You can see whether all are single phase or multi-phase. So that's what we have done here. And of course, we have done XRD as well. XRD is wherein instead of electrons coming, you put X-ray on the sample. If you put X-ray, then they diffract based on Bragg's law, and lambda equals 2d sine theta, right? So based on Bragg's law, you get different peaks reflected from different planes. So these different peaks are signature of different crystal structures. And in this case, it's a hexagon. Sorry, it's a monoclinic, right? At high temperature, it's monoclinic, and it's orthorhombic. 5,4 is orthorhombic, and when it's orthorhombic, you have lots of planes, so you get this really complex peaks, and it also has small phase of 5,3, small phase of 1,1. So this is what we want. That is the major phase, but there is some impurity here. Okay, so those peaks we can see. The red is 5,3, the blue is 1,1. Okay, so that means when we did ball milling, we changed the chemistry a little bit, and we got some impure phase, right? So this is how you characterize the powder, so that when you use it in additive manufacturing, you get the material you want. Okay, and again, here is the reference peaks of different phases. When it is you don't clean the signal, this is how it looks like. And when you remove the noise, you get slightly better signal. So if you remember, in my first class or second class, I was showing the peaks of simple cubic, SiO2, and other materials. They were only 3 peaks or 4 peaks clean XRD signal, right? That's not possible with crystal structures that are hexagon or orthorhombic or monoclinic. So here is more SCM images. Here we size separated them. These are bigger particles. Their average size is 780 nanometers, 610, 560, 300 nanometers, and these are really small. We basically, it's a very simple process. What we did to size separate them was we mixed them in ethanol, and then we sonicated them. So now they're well mixed and has all sort of particle sizes. Now we put it down on a magnet. So what happens if you put a magnet and put these particles? They will all be attracted down, right? But which one will get attracted down quickly? The bigger ones. So within 1 minute, all the bigger ones come down. So we quickly remove the liquid and take the residue, that is bigger particles. And we sonicate again, and now we keep it on the magnet for, instead of 1 minute, do it for 5 minutes. Then we get next. So this is a simple size separation technique. Okay, so we get, and when we image them in scanning electron microscope, we confirmed that we have size separation. And this is TEM images. So here you can see this is a particle, and you see this is amorphous, this is crystalline, right? These are signatures of crystalline material. These are basically your atomic stacks. Okay, so here what this is showing is, here it's a big particle that electrons did not go through. Here electrons went through, and here also they went through. So this is amorphous, this is crystalline. Here the electrons did not go through. What this means is this amorphous is an oxide. It's not, or it's an oxide is formed. Gadolinium oxide or gadolinium 203 has formed. Here it is gadolinium silicide. Okay, so that is transmission electron microscope. So that means for transmission electron microscope, you need to make a sample that is 100 nanometer thick. Then only electrons will go through. In scanning electron microscope, electrons come and rebound back. In transmission electron microscope, electrons transmit through. Okay, so this gives you better resolution like this. So you can see whether it's crystalline or amorphous. There, the resolution is not that great. Okay, you see this is 5 nanometer, this is 500 nanometers, right? So once we did that, here is the magnetic properties. This I have already shown. If you mill for longer duration, you lose the magnetic property of the material. So you have to be somewhere here where you have highest magnetization for 20 minutes. But if you do only for 20 minutes, you may not get smaller particles. So how do you get smaller particles and still retain high magnetization? Is by adding some media called milling media. So it basically distributes the energy, and then you get smaller particles, but you get higher or similar magnetization. So here, if you look at these different size separated particles, they have different transition temperatures. Okay, so that means if the magnetic or if the particle size changes, their property also changes. So that's why you need to retain or size separate the particles. And same thing here. So the red one is the 40 minutes milled particles, and the black one is 20 minutes milled particle. So 20 minutes milled particle is similar to the bulk, whereas red has lost most of its magnetic properties. Okay, so now we have the powder. We also have different particles. Um, so now we can use these particles to do additive manufacturing, right? So the beauty of this, the particles is because now if you want different magnetic properties, you can take different sizes particles and use those different size particles to get different properties on your component that you 3D print. Okay. So here we are showing more. So here you see it's not 20 or 40 minutes. Here we have milled them for longer duration. That's when we have used milling media, we were able to mill them for longer duration so that we get good particle sizes, the ones that we expect. So in this case here, 50 minutes gave us 780 nanometers, and 96 hours gave us 300 nanometers. Okay, so here is how their properties change. When the particle sizes change, the magnetic properties also change. Okay, here this is hysteresis curve. Basically, we applied high magnetic field in positive direction and negative direction. Here we just changed the temperature and measured its magnetization. So we get, this is the transition temperature here, which is close to 340 degrees here somewhere. So this is for S1. This is, sorry, not 340, it's 310. And the smaller particles have smaller and smaller, or lower and lower transition temperature. Okay, so basically we thoroughly characterize the particles. That's what it means, right? So now we have particles whose properties we understand. We can side separate them and know what is the magnetization of each different particle sizes. Now, this work goes back to 2018 and 19. We published, by the time it was published, it was 2020. But so back then, we did not have access to good 3D printer. And even if we had, the materials we were making were very small amount. So we had to come up with some other 3D printing technique. In here, we just looked at inkjet printing. So when you inkjet print these and measure the properties, we started to notice that if you inkjet print them without applying any magnetic field, you get something called coffee ring effect. So what that means is when you drop the material and the material dries out, the outer border of the particle becomes coffee ring like. So when you x-axis, or we call it a-axis, right? This is b-axis, and this is the C of the crystal, right? So a lot of the times, if you measure Young's modulus, electrical conductivity, thermal conductivity, or the magnetization, the long axis tends to be easy axis, meaning you find higher property, higher conductivity, higher magnetization or magnetic permeability, whereas the smallest axis will have lower, right? So if I, for example, do the magnetic property measurement on this, if I apply field here and measure the magnetization, a-axis will look like this. So not a-axis, this is b-axis. Whereas C will look like this. Sorry. I'm thinking something and saying something. So A is the hard axis, B is the easy axis. Okay? So if you have a polycrystalline, what will happen? This is a single crystal sample, right? This is called A-axis is the hard axis, B-axis is the easy axis for magnetization. You don't call it easy and hard for other property measurement. For example, thermal conductivity or Young's modulus or electrical conductivity. You just say, oh, one axis has high property, other axis has low property, right? But if you take a polycrystalline sample where crystals are randomly oriented and measure the property, what will happen? Where will you see? It will be somewhere in between. This is polycrystalline. Okay, so this is B-axis, A-axis, and this is polycrystalline. Okay, so that's what it looks like. When we don't align, when we don't apply magnetic field, we just got in between, random. Whereas if we put it in one direction, we got the easy axis. In the other direction, we got the hard axis. Red is in a lateral direction or normal direction. Black is the parallel to field direction. And when no magnetic field is applied, we get blue. Okay, so did you look at 3D printing with applied magnetic field or electric field? Where you, or did you study in the class? Did Dr. Somshekhar cover how you can apply magnetic field or electric field or stress to align the okay. So this is what you can do for functional materials. You apply magnetic field or electric field or some stress, you can change the properties of the materials you 3D print. Okay, that is the beauty of 3D printing functional materials. That's why it's called 4D, because 3D is XYZ and 4D is the function. This is the property you can use. Does that make sense? So this is one of the tricks you can use when you're 3D printing functional materials. Apply magnetic field or electric field or stress to get the property in a specific direction, or to get the property you want, or to change the property the way you want it. Okay? So it has really nice applications, because now I can enhance my 3D. If you do regular processing, right? And if you 3D print in an applied magnetic field, my 3D printed materials or components will perform better, because I apply magnetic field when I'm 3D printing, than the normal processing, right? So that's the advantage. So that means you can see here we also calculated the entropy change, which is the cooling effect, or the heating effect of the magnetocaloric materials. And the black one is where the magnetic field is applied. Blue one, no magnetic field is applied. The red one, we applied the magnetic field in the opposite direction, or in the hard direction. So we can change the properties based on how you apply the field. And now you don't have to go to the extreme here, right? One gives you really high, one gives you really low. You can be in between by changing the direction of the magnetic field, because you can now change the direction of the field, right? You don't have to just stick to 90 degrees or 0 degrees, parallel, perpendicular field. If you change the field in a specific direction, you can vary the property in between, right? So we can use that to create a lens. These are called green lenses, gradient refractive index lenses. So that means you can change the refractive index of the material in a way where you can make it like a lens. So that's what this paper reported. And they were able to make a lens. If it's a regular, the refractive index is all equal in the material, then the light just passes through. Of course, you can machine the glass to change the signal going through. Here it can be optical signal or electromagnetic signal. Okay, if it is electromagnetic signal, then it's not, glass won't work, right? It has to be magnetic lenses. Then you can change the permeability of the material based on the direction of the applied field when you are making it. Then you can create some lens with certain focality to it, and make the signal go through in the way you want. So this is another application where you can use applied magnetic field or electric field. It can be electric field, magnetic field. It can also be stress. Okay, that will change the properties in a specific pattern. Here you can see if the particles are aligned in, then you get non-aligned, you get this. But if they are radially aligned, you get this black. If it is circumferentially aligned, you get the dotted ones. And then you can get anything in between. And that small variation is sufficient to change the refractive index of the lenses. Or you can, for magnetic lenses, you can also change the permeability. So now let's come back to the magnetocaloric refrigerator. So now we want to 3D print the material, right? So why do we want to 3D print the material? Because we want to cool it down efficiently and not wait for too long, right? Because if it's a bulk material, it will heat up and it will take long to cool down. So we want to make microchannels so that we can cool it down quicker, and then uh, extract the heat even further when we remove the magnetic field. So some people, people were trying plates so that you can send the water through. That is one way. You can just make the plates of magnetocaloric materials and extract the heat before removing the magnetic field. Or some people made just compact powders with pores. That's another way. But if you have the ability to create microchannels, you can actually remove the heat more efficiently. The problem here is when you have a magnetocaloric material, the entropy change depends on the amount of the material as well. So it's a volumetric effect. More the material, higher is the entropy removed, or higher is the cooling effect. So if you remove the materials like this randomly, just making the plates or making the pores, you are basically removing some of the cooling effect, right? So you want to have efficient heat transfer, but at the same time, you want to have the maximum material as possible, right? How do you do it? Now you have to do some optimization studies, you have to do some modeling and come up with the structures where you have just enough channels so that you remove some material but not too much. So you have to get that optimal value where the amount of channels is just sufficient to remove the heat, but you don't take out too much material. Okay, so this might be too big pores, but this was one of the structure that was printed using other magnetic material in Ames lab, using lens system. Okay, so you can also do, when you 3D print, you can also do functional or compositional grading. So I talked about different particles can have different magnetic properties, right? Different size particles will have different magnetic properties. So now you can 3D print different size particles in a gradient pattern. By doing that, you can change magnetic properties in a gradient pattern, just like I showed you in the lens. So by doing this, you get gradient effect. So it's called functional grading. Okay, so by doing this, you can improve the efficiency of magnetic refrigerator, magnetocaloric refrigerator. So this is how you get the magnetocaloric effect: small, high, high, and maximum here, depending on the composition or depending on the particle size of these materials. Okay, so that is called compositional grading, which leads to functional grading. So we, after binder jetting, we used another technique called direct ink writing method. So this is, we also call it bioplotter. Basically, we make a slurry. So take the particles, put it in a binder, make a slurry, and that is printed using high pressure nozzles. But this makes three-dimensional structures, unlike inkjet printing. So this is called bioplotter. Okay, so you can, so you use binder material and use pressure and a small nozzle to print a specific structure. So this is inkjet printing, and this one is printing. I don't know if you are seeing, it's printing three-dimensional structure in the bioplotter. The one we bought this in 2018. I don't know if you are able to see. So I should have made a larger video. But anyway, so here this is inkjet printing, and this is direct ink writing. Although it's ink writing, but it makes 3D structures because we use slurry material, and that it also evaporates immediately after printing. And again, this is what I talked about, composition grading. We can use multiple nozzles to have different grading, which will lead to different functional grading. And this is what we printed. The channels were 200 to 400 micrometers here, and these are different structures we printed. One of the problem here is they collapse. You can't print taller structures with this. This is one of the disadvantages of direct ink writing technique. But direct ink writing is much more simpler. You don't use any laser or wire arc or powder bed. So this is where you make a slurry of the material and use a nozzle, high pressure, and just control where you print, right? This can also be used for normally it's used for biomaterials, like if you want to print a scaffold or a skin structure, this is what is used, okay? Instead of the slurry of nanoparticles, magnetic nanoparticles, you use cells to print, okay? So that is bioplotter. It's nothing but direct ink writer. And here we show the precursor powder has slightly high magnetocaloric effect compared to the. So once we print this, that's called the green body. And now we take the green body and we have to sinter it so that we remove all the binder in this. The glue that we put, which is binder, we heat it up and burn it off. So, and we do it at a temperature where particles also fuse together. So that's called sintering. And we sinter it, and the sintered part has slightly lower magnetocaloric effect compared to just the powder, okay? Which is as expected because the sintered part has some binder material left out, and the precursor is pure material without any binder, okay? And now we put these regenerator in the magnetocaloric refrigerator. This is what we built in our lab. It was not very efficient one, but it was sufficient for us to characterize whether we can get better heat transfer efficiency using these microchannels. Okay, so that's about magnetocaloric additive manufacturing or additive manufacturing of magnetocaloric materials. The next one I'm going to talk about is how we use additive manufacturing to make these coils, okay? So these are, I talked about brain stimulation, right? Using magnetic fields. And those are quite widely used. And the commercial one looks like this. If you take an X-ray of the commercial one, this is what we did. We were not supposed to do this. We were asking asking Maxim to give us the dimensions, the pitch, the distance between, the diameter, the thickness. They said, no, it's a trade secret or something like proprietary information. We can't give that. So we just took it to our micro CT scan and imaged this coil. This is the same coil. And got the, so we needed this to model how much magnetic field it generates, right? So this is all copper winding. This is nothing fancy here. There is no magnetic material. It's just copper winding that applies large magnetic field and makes the neurons fire just below the coil. Now we started using magnetic materials. You remember we started using ferromagnetic cores here so that we make the flux go to, did I talk about that? How we use magnetic materials to change the flux so that we can go to a smaller area. So these are their commercial coils. In all these coils, there is no magnetic material. It's all copper windings. Right? This is all copper windings. So, but we know, so the magnetic researchers know, we can change the way magnetic fields are directed by using magnetic material. If you have high permeability, all the magnetic field will come through high permeability material, right? So if you put a core here, all the field, instead of going below the coil, it will go through that core, right? So there is a lot of work on just the structure of the coil without using magnetic materials. So we decided to use magnetic materials. We also did some coil configuration without using any materials because that was the trend, right? And also it was difficult to put magnetic materials within already existing coils. So we designed different coils as well without any magnetic materials. This is another coil. So now, if we use a magnetic core, which has high permeability, a ferromagnetic core, when these coils when these coils generate a magnetic field, all the field will go through these cores, right? It won't disperse away. It goes through these cores. So if you have different coils like this, through one core, you can get the magnetic material. And if these are turned on, you get a smaller area of stimulation. If you turn on these two, you get it here, okay? So now if we have this kind of coil configuration with magnetic materials in all these coils, we can actually make the magnetic field to go through that ferromagnetic core instead of dispersing, okay? So we had to, the advantage of making so many of them and controlling them independently, these are so many cores, you can control them independently. And if you control them independently, then you can actually move the stimulation site to different area. So you can stimulate first here, and then to auditory cortex, motor cortex, and so on and so forth. You can also do two sites simultaneously with this kind of configuration. Okay, so, but in order to test this, we have to first, this is a modeling work, we have to first make one coil and make sure we are able to focus the coil to one area and generate sufficient field to make the neurons fire in a small animal like rat, okay? And we did that. We built our own stimulator. We used this high permeability ferromagnetic core and stimulated the rat to get a twitch in its limb, and that is the motor evoked potential. So now we showed that yes, we can use one core with a small current and focus it to get the rat twitch its leg. right? So that's the work we did using ferromagnetic core. But the problem here is, you see the amount of twitch. It ends up stimulating the entire motor cortex, not just one leg or one hand or one finger. Okay? So if you want to be more focal, then you can't just have a simple ferromagnetic core, a cylinder or a cone shaped tip. You have to make the material more core slightly more complex. So we did a lot of design iterations. There was this one published as well. This is single core. And then we realized that a core like this in a hyperbola with V shape like this, at this tip, you get really focused fields here. And that focused field can stimulate either the hand, leg, or a finger. You can make it more focal than a single core. Okay? You can see here how we can make the field more focused. That's a simulation study. And then this is just the ferromagnetic material. We knew how to improve further by using diamagnet. Does anybody remember what's a diamagnet? We know ferromagnetic core, if there is a small field, it goes through ferromagnetic material, and the magnetization of the ferromagnetic material goes up, right? What's a diamagnet? Opposite to, yeah, it repels the magnetic fields, right? So if you put a diamagnetic material surrounding this, so it will deflect all the unwanted field. So we made basically a hole, a plate with a hole, and that hole is left just here, and the plate, because it's diamagnetic, it will deflect all the unwanted fields coming on the other part of the brain of the rat. Okay, so here we show, if we use a complex coil like this with a diamagnetic plate, you get the more focused stimulation compared to no diamagnetic shield, or compared to double C coil like this. Double C is the yellow one, whereas the blue is where it's a commercial coil, where there is no this one, A, there is no ferromagnetic core. Okay, that is blue one. So it ends up stimulating all the surrounding areas. Okay, so, and this is V-tip. V-tip is a little odd. Don't worry about that. So just look at these four cores, or four coils, and this one, green one, is the best. That's because we used two magnetic materials, one to deflect the fields and another to focus. Here it focuses, and the deflection plate is somewhere else, which we have not shown. Now, how do you make this structure? So you have to take a bar, machine it like this in a V shape, bend it like this, right? But then the magnetic material that has high permeability will not bend like this. Look at the curvature. It's impossible to bend unless it's gold or it's very malleable or ductile, right? So this was not possible because it's not that malleable or ductile. So we had to change our shape to something like this. Of course, the performance reduced a little, going from here to here, right? Now you wind the coils to generate magnetic field so that it goes through this point, which is focal. Okay, so we did that, and we characterized. This is Hall probe, which measures the magnetic field. When you do that, you get a small focal area, and we tested this on the rat. I don't know whether you are able to see the rat. This is the rat. Okay. So the problem is we are not able to make this shape with regular machining. So what do? You have to 3D print it, right? So that's where we took, that material is called permander. It's an alloy of iron, cobalt, and vanadium. So we took iron, cobalt, vanadium powder, mixed it together. This was done right here in lens system. Okay, you have seen this, right? So we made a composition. First, we had to make a material of the right composition, right? Because these are 3 different powders. So we used these powders and made a permander magnetic, ferromagnetic material. And this is how we just first, we're not interested in the shape, right shape now. We want to get the material right first. We want to get the properties right, right? Get the right composition, right crystal structure, and right magnetic properties. And these blobs are the samples that are printed with basically different laser energy, different feed rate, so that we can see how the properties change. And once these are printed, we looked at their XRD to make sure we have the right crystal structure, and yes, we do. Now you see how there are only 3 clean peaks. And can you tell me why we only have 3 clean peaks compared to the, sorry? Cubic structure, simple, highly symmetric structure, which is cubic, right? But if you had orthorhombic or monoclinic or hexagon, what will happen? It will be populated with so many other peaks. Okay, so we got the crystal structure right just by mixing the powder and using the lens, right? Now let's see. This is optical microscope. This is also optical microscope. Is this optical microscope? This is optical, I know. That is optical. This is SCM. Okay, this is EDX. Okay, energy dispersion, X-ray dispersion spectrometer. Okay, so EDS or EDX, and here we do elemental analysis to make sure we have the right amount of right composition of the elements, which we do. Okay, so this confirms that we have the right composition, right crystal structure, and we have some multiple phases. I'm not sure whether this is optical or okay, yeah. So this is SEM because you see the resolution 100 micrometer. That's 200 micrometer, and we have multiple phases here. Multiple phases means you may have the same crystal same composition, but slightly different crystal structure, and that might show up as different phases. But we have the right crystal structure because we don't see any other peaks, right? So this could also be due to different height variation. When there is height variation, you get different contrast. Okay, that doesn't mean it is different phases, but it's just different morphology or different contour on the sample. So anyway, we went ahead and did the magnetic measurements. So this is 9 samples, some are missing. And when we look at this, the commercial one is black here. This is the commercial one. And if you look at the commercial and some of the 3D printed ones with the right parameter, they were very close. But the blue one did not, it has lower slope, meaning lower relative permeability. So we should not be using these parameters. Blue corresponds to sample number 6. Sample number 6 had these parameters. So, but the problem there was we could not establish a pattern. Okay, usually if you increase the laser energy, the slope decreases or slope increases, right? That's a right pattern. If we come to know, we now know exactly how to tune the properties of materials, right? By just changing the energy of the laser or changing the feed rate or scan speed, right? So, but we could not establish a clear pattern, but we got a composition that is close to the commercial material, meaning close to the original material, the one that we checked or the one that we machined, right? So this black one is commercial sample. And so here are the pallets that are 3D printed. So this is a commercial sample that came from our coil, which we made, that did not show nice field focus. And these are the 3D printed. So we had to just put them in a tube with these Teflon tape. And these are all different samples. This sample is a FDM printed plastic sample, ABS. So now we used powerful X-ray. It's called CT scanning. This is micro CT scanning. No, we did nano CT scanning. So when you do CT scan of these samples, if there were any holes or pores, you see. So the plastic completely disappeared, right? So plastic, that means it did not offer any resistance to the X-ray, high energy X-ray beams. Whereas these samples that were 3D printed here looked similar to commercial sample. That's the commercial sample. Okay, so that means in terms of density and packing factor, we're getting good density, good packing factor. In terms of crystal structure, we got a clean crystal structure. In terms of composition, we got right composition. So we got everything. Now we just need to vary the parameters so that the feed parameter or the laser energy, so that maybe when the crystal structures are formed, they are larger in size or smaller in size to match the magnetic properties of the commercial sample. Okay, so that's where we have stopped. Now the next step is to make a big structure and wind the coils and test it on a rat. Okay, and make sure it has that high focality. So that's the 3D printing of ferromagnetic cores for brain stimulation, right? So now you see the connections, right? So we are taking a 3D printed magnetic core to stimulate the brain of a rat. Okay, so we still have to figure out how to. There will be some issues because when you print a large structure like that, there will be issues with crack formation. It may not form the entire nice shape. It's also quite tall, right? So if it was not tall, it would have been okay. But if it's quite tall, you may have, the bigger the material, the more higher chances of having defects. It's as simple as that. Okay. So now, I think that's the end of the class for 3D printing functional materials or additive manufacturing of functional materials. But I just want to remind you again from my first class, this is VCU. Of course, IIT Dharwad wants, if you are really interested in doing PhD or master's, IIT Dharwad is a good choice. But if you are interested to do it abroad, VCU is also a great choice. Okay, here are some of the salient features of VCU. So it has great programs, great infrastructure, great facilities, large expertise. So we boast ourselves of having a Nobel laureate and lots of highly accomplished researchers. We have 36 research centers. So please consider VCU as an option if you want to do master's or PhD abroad. Okay. With that, I can answer any of the questions you have in 3 minutes, 11 o'clock. Or we can take a few more minutes after that too, because we started late. Any questions? So that's a good question, but that's the fundamental of our work. So the way magnetic field stimulates our brain is using Faraday's law of induction. So if you have a magnetic field, AC magnetic field, or time varying magnetic field, by Faraday's law of induction, it induces currents in the conductive parts. So if you take a solenoid coil and apply AC signal and place it on any metal, you can introduce currents in that metal. That's how the transformer works. So the nerves are the conducting part. So now you have, but that's a very crude way of explaining. It's way more complicated, okay? Because nerves are not like conductors, like copper wires, right? Nerves are biological materials, very complex in nature. Nerve have membranes that have what is called as voltage gated ion channels that let calcium and potassium ions in and out, sodium, calcium, and potassium ions in and out. And by controlling this density of the ions, they conduct or they make neurons fire. So it's called electrophysiology, study of this, how you stimulate brain or how you record brain signals. Okay, it's complex, but in a engineering sense, it's Faraday's law of induction. So just like transformer, how you upregulate or downregulate voltage, right? In a transformer, we are doing the same thing. We are sending magnetic fields into the conducting part of the brain, which is neurons. And once the voltage crosses certain threshold voltage, then it fires. Yeah? Any other questions? On additive manufacturing of functional materials, you can ask, when you have seen now the 3D printers, you know what are functional materials. And I even showed you one example, which is done here. So what other materials can you 3D print that are functional? Okay, what are functional materials? Which are the other functional materials? I showed about magnetic materials, right? We had a separate class on piezoelectric, so you can 3D print piezoelectric materials, right? But the problem with 3D printing piezoelectric materials is they're ceramics or polymers. So they are ceramics, and we also have polymers. Yeah, PVDF is a piezoelectric material, that's a polymer, right? So you can 3D print polymer, but the ceramic becomes a little difficult, right? Because ceramic materials, you can't melt them. Their melting temperature is so high. You might have to think of other way to sintering method to 3D print them, right? So ceramics melting temperature is high. So 3D print using laser, you might have to have high laser energy, right? And then normally ceramics are oxides, right? And now, are you able to make the exact oxide or not? Are there different phases? Whereas metals, you don't make any oxide. You control the environment and you are good. It should make the right phase, right? Any other questions? So think of 3D printing piezoelectric materials. It will be slightly more complicated, right? And if you want to align them, you use electric field, not magnetic field, right? So it's a quite interesting area of work once you've, and again, it's also new. A lot of people are trying to do it. Um, and if you do it right and get the desired results, um, you can directly impact certain area of research or a certain application. Okay. Um, any other question? Yeah, okay. Did you do the assignment? Oh, there's a, yeah. You did? So you watched the video? It's okay. I'm just, yeah. So you watched the video, right? So what do you think about it? So he was the PhD student when he was able to figure out the process. He was a senior PhD student, but the white LED that you get, you can, yeah, thank him for that. Right? Okay, sounds good. If you have any other questions, I'll be around. And today is the last day. I'm flying out today. So yeah, I'll be here uh, until 4 p.m. maybe. Yeah, if you have any questions, or you can also email me. Right, thank you.